All right, let's talk about the key concepts of kinematics. So we have these three equations, which are our equations for uniformly accelerated motion, and we have independence of motion. So these three equations, I can't really explain them other than show them to you and how to use them in problems, which I'm going to do immediately after this. Um, and then we have one excess problem that would be more like vectors, which is a part of kinematics. Um, and then we also have independence of motion. So the entire idea behind independence of the motion is that whatever happens in the x direction does not affect the y direction. Whatever happens in the y direction does not affect the x direction. And then there's also a z direction in there because we live in a three-dimensional world, but we don't deal with a z dimension in physics. So we are talking mainly about two-dimensional motion where we have an x and a y. So if we have an acceleration in the x direction, it will not affect the y direction. Hence why all of these equations have for things that matter in direction, x is by them. So you have velocity x naught, and then acceleration x, and then also distance in the x, meaning that if we have an acceleration in the y direction, like gravity, it won't affect things in the x direction, which are very important for projectile motion, which I'm about to show you. So let's talk about how we would solve this first problem. We have a ball thrown at an angle of 30 degrees and with a starting velocity of 20 meters per second, distance and max height. I forgot to put the knot on that one, but I'm sure you guys will live. So we have it being thrown at 20 meters per second at an angle of 30 degrees. What's the distance and max height? So first of all, let's think for a second. We have the only other thing that would be acting on this would be gravity at any given time, and gravity moves straight down. We can't really change the whole thing about gravity moving straight down. So let's just convert all of this into x and y forms, so that way we can better do these problems. So we have 20 meters per second, and 20 meters per second, we know that if we wanted to solve for any angle of a triangle, we can use sine and cosine. So that means that this side here would be 20 sine 30 degrees. Sine of 30 degrees is 1/2, which means that this height here would be 10. Um, we know that this side here would be cosine 30 degrees, which would be uh, cosine of 30 degrees is rad 3 over 2 times 20, which would be 10 rad 3 meters per second on this side, meters per second on this side. This is velocity not y, this is velocity not x. So now that we know all that, let's state all of the given knowns. We know that velocity not x is equal to 10 rad 3. We don't need to put units because these are all things that we refer to, not our answers. V naught y is equal to 10 meters per second, although I don't need to put units, they just said we don't need to. Acceleration in the x direction is equal to 0 meters per second squared. We have no other correlation. I don't need to do units. We have no other correlation with this here. You guys can still see it. Yes, you can. So we have nothing affecting it in the x or y direction. If this said there was wind, sure, it would. And then they would tell us what the acceleration due to that wind is. But because we don't say that, and because we're going to assume negligible air resistance, because air resistance involves calculus that we don't want to do, is equal to 0 then. So acceleration of the y is equal to gravity, which if we set our positive direction upwards and then to the right, because that's just the directions that they start with, for our velocity, we can say gravity then is negative 10 meters per second squared. Of course, we can just use 10 for gravity at all times. So then we also know, we want to know our distance, and we want to know our max height. We want to know our distance and our max height. So let's solve first for the distance. So if we were trying to solve for distance, the first thing we would need to do is figure out how much time this thing is in the air for. Because if we try to solve for distance immediately and go straight to the equation for v naught x, then there's nothing that pulls us back down to Earth. So for all the ball knows in the x direction, it will move this way for all eternity. But then, of course, if you talk about the direction in the y, it would start up and then go back down, or really it would just go like this. up, and then back down if you're talking about independence of motion. So we want to figure out how much time this ball is in the air for using the y direction, and then plug that time in for the x direction, and then solve for our distance that way. So let's think for a second. We're starting this ball at 0 meters above the ground, so we'd have no starting height. So that means if it's hitting the ground again, we have no change in height. Now this x, of course, could also be x, or it could be y, so height. So we have 0 change in height is equal to initial velocity in the y direction, 10 times time, plus, actually, you know, I'm just going to also write down the initial equation that we're going to use to plug it in, because the AP test graders will love you if you do that. If you spend the time to write down the nuanced equation of it all, it makes their grading job easier, and then also puts them in a better mood to want to grade your test with a better score. So we have 10t plus 1/2 ay, so negative 5t squared. Hopefully you can do that mental math. And then we know 0 is equal to, we can pull out a negative 5t, negative 5t times negative 2 plus t. So t minus 2, in other words. So the things that will make this equation equal 0, t is equal to 0, of course, because it's at the ground at 0 seconds, and then also 2. So that means t is equal to 2 seconds. That's how long it spends in the air. So now that we know t is equal to 2 seconds, let's plug it back into our equation for distance in the x direction. So we'll go distance in the x is equal to v dot x times time plus 1/2 ax t squared. We know that ax is equal to 0, so we can completely negate this entire term here. So distance x is equal to v naught x, 10 rad 3 times our time, 2 seconds. Distance in the x is equal to 20 rad 3. Of course, you can give them that as an answer, because that would be a completely simplified answer, but we also know that distance in the x is, if I can type with my calculator correctly, 20 rad 3, which would be 34.6 meters. So distance x is equal to 34.6 meters. So then we can say distance x is equal to 34.6 meters. Let's say it one more time, 34.6 meters. So now to solve for height, you'll see why I'm about to do this, but I'm only going to erase this portion here. So if we think about how an object moves that starts at 0 and then ends at 0 again, and then goes up or down after or before then. I'm going to move this little dot over because apparently I didn't draw that where I wanted it to. This motion can be modeled with a parabola. Now, if we know how parabolas work, we know that the distance halfway through is, you know what, I'm actually just going to draw this with a graph. So we're going to take a graph of distance upward, or distance versus time. So if we have a distance versus time graph, and we model this based on time, we would have something that looks like this. I'm going to move it over again. We'd have something that looks like this. So this is kind of like the flight path versus the time. I'm not going to say distance, I'm going to say flight in both the x and y directions versus time. So as time progresses, this thing gets higher and higher, reaches a peak, and then gets lower and lower here. So we know that it gets lower here at 0 and 2 seconds, and we know it reaches a peak here. Well, if we're talking about a parabola, we know that if we draw a straight line through that parabola, similar to what our x-axis is doing, that these 2 points here, if we draw another line that goes straight through the vertex, these 2 points here, there and there, these 2 segments here are equal to one another, which means if this is segment x, then this is also segment x. Same applies to a flight versus time diagram. So if we know that the maximum height is the point that would be a vertex on this thing, we can draw a line that goes through here. We know this entire thing is 2 seconds to get flight. We know that then where it reaches the maximum height is at 1 second, half the amount of time. And that stays constant for all times where you start and end at the same height. It is key that you remember that it only does this when it starts and ends at the same height. If for some reason we said that this ball was thrown a meter above the ground, we can't do this because then we get skewed. We start out here and then end down here, meaning that there's a little bit extra time right here that there is flight, which means it's not half. Half will put you like right here, not at the maximum. So we know then that we're looking for half the height in order to get the y maximum. So we know change in y maximum is equal to v naught y times the time but halved plus 1/2 acceleration in the y times t 1/2 squared. So, and I put those 1/2s in subscript to then denote that I'm dealing with 1/2 of the time. So we know change in y maximum is equal to v naught y, which is 10 times the time square, or half the time, which is 1 plus 1/2 negative 10, and then 1/2 the time, 1 squared. So we know change in y maximum is equal to 10 minus 5 meters. So 5 meters. And that would be our solution to this whole problem here. Now, with that being said, we can erase this and then now move on to the next problem. A box slides on a surface with no friction at an initial velocity of 2 meters per second, then reaches 18 meters per second after 4 seconds. What's the acceleration and how long does it travel for from 0 to 4 seconds? So now we got to use these equations again. So a box slides on a surface, starts out with a v naught is equal to 2 meters per second. It's always nice to make a list of our beginning equations because there's so many different variables here. We don't know which one we want to use. So and then it says it reaches 18 meters per second at the very end. So we know a velocity final. After 4 seconds, time is equal to 4 seconds. So we know a time, and then we're looking for an acceleration. So this one talks about, or we're looking for an acceleration, and then we're also looking for a distance. But I'll tell you now, we're going to look for the acceleration first. So there's only one equation that models all of this stuff. That one equation being this one. So without any extra stuff, because these two here have a distance, and we don't know a distance. So this is the only one left. So we can plug everything in here. We have a final velocity, or actually no, let's write the equation first. Velocity, we know we're only moving in one dimension here, so we don't have to put an x or y. Velocity is equal to v naught plus a times t. The 18 is equal to 2 plus acceleration times time. Time is equal to 4 seconds. So 16 divided by 4. Acceleration is equal to 4 meters per second squared. Acceleration is equal to 4 meters per second squared. Now we get a choice. Do we want to use this equation or this equation? Because we know, or this equation or this equation, because we know everything for both of those equations in order to solve for it. But because this one would give us a more exact thing, I'm going to use that one instead. Also because we've used this equation a bunch already and I want to model using this one. So we know that our initial velocity, or our final velocity, is 18. So 18 squared is equal to 2 squared plus 2 times acceleration 4 over the distance change in x. So let's put this all in our calculator. 18 squared minus 2 squared. Keep in mind that we can't then just divide it by 2 squared plus 2 times 4 because those are two different terms. So we have 18 minus 2 squared is equal, or 18 squared minus 2 squared is 320. 320 divided by 2 times 4 is 8, or dividing that would give you 40. So that means our distance in the x is equal to 40 meters over the time frame 0 to 4 seconds. So 40 meters. And then we can actually verify this using that other equation. That's the good thing about having two equations to choose from, is that we can then verify it. So we can say 40 is equal to V naught x, or V naught 2 times 4 plus 1/2 4 times 4 squared. This side should equal 40 if we're done with it. So 2 times 4 plus 1/2 4 times 4 squared. It would be super awkward if that didn't equal 40. And it does. So we're fine. So we know then that our acceleration is 4 meters per second squared, and our distance over 0 to 4 seconds is 40 meters per second squared, or 40 meters. So now we have a boat crossing an 80-meter river with a current of 3 meters per second perpendicular to it. That sign there, upside down T, means perpendicular. What's the maximum maximum velocity of the boat is 5 meters per second. What angle should it go at for a straight journey, and how long would that journey take? So this is actually a really good problem. So we have a river here that has a distance of 80 meters. And then there's a current that pushes everything downwards at 3 meters per second. Okay? And then we also have a boat that's trying to cross this river where its maximum speed is 5 meters per second. Oh, nice. There goes the cap. So we know then that if we tried to, let's just interpolate here, what direction should we take? If we were trying to model this thing in real life, we could use the example of trying to throw a ball into crosswind. So if we were trying to throw a ball to a friend, we have a little bit of distance here to him. If we were trying to throw a ball to a friend where we have wind that moves, or wind that pushes this ball from right to left, we would then have to throw this ball to the right so that it would curve towards him and use the wind to then make that straight path. So we can model this initially with a triangle, because everything turns into triangles. We can model this initially with a triangle. We have a downward push of 3 meters per second, and then we have a maximum speed of 5 meters per second that's going to be at some angle. It's not going to be here because our maximum speed would be including that angle. If we said our maximum speed was going straight this way, then this here would actually push it down further here and make it not a straight path. So we have to model it as if it were. And then now we just have to solve for this angle here. So we can use the inverse sine to solve for that one. Inverse sine of 3 over 5 is equal to our angle. Plug that into our calculator. I think it's 37, just because I've seen this one before. 3 divided by 5 is equal to 36.869. So I'm going to call it 36.87 because I like to be exact with the numbers if I can. So our angle is equal to 36.87 degrees. Because if you're more exact with the numbers immediately, then you get more exact answers at the end, and you don't round it off and then miss the problem because you rounded it off an extra hundredth of a digit, which would be a super lame way to miss a problem. So if this is our angle, 36.87 degrees, that's our answer for the angle. So I'm going to put it up here. Angle is equal to 36.87, just because I'm going to erase this a little bit. So now that we know that, we need to know how fast it's going to travel along the straight path, because we're trying to find the time it takes for the journey to go. So if we know now that this angle is 36.87, then we can do one of two things. We can then just use tangent or cosine to solve for this angle, or to solve for this measurement here, or we can just recognize that this is actually a Pythagorean triple triangle and that this is a 3, 4, 5 triangle. So we would have 4 meters per second here. So that means it would be 4 meters per second trudging along as it goes along the river that is 80 meters wide. So that means we can use one of these equations to solve for it. We know a distance, we know a speed, and we're trying to look for a time. So a distance, a speed, and a time, a perfect one to do, or a distance that stays a speed that stays constant, rather. So let's use this top equation here. 80 is equal to, or let's model it. So change in x is equal to vt plus 1/2 at squared, although there is no acceleration, so we can take it out. Sure, acceleration from this thing, but no, because independence of motion tells us that acceleration doesn't matter if we're talking about a direction perpendicular to it, and it is perpendicular to it, so there is no acceleration. 80 is equal to velocity 4 times the time it takes, so it would take 20 seconds for the boat to cross the river. And with that being said, we have solved for our kinematics, and I hope that that's a good touch-up on kinematics and whatnot. So let's also talk just for 1 second about how vector addiction. Wow, I've been in English class too long. So if we talk about how vector addition works, we could also say that we have a vector here where the boat starts here. It has to travel 5 meters per second length vector up there. And then it has to travel, and then because of the current, it must travel 3 meters per second down here, and then form a line that goes straight perpendicular to the thing it's going to, perpendicular to the bank of the river. That's the word. So if we know that we have two vectors here, then this is just a triangle, and we're adding vectors where this here is some angle, the angle, and then this here is some speed that goes just straight across. So that's just a touch up on vector addition. We can also talk about that in different subjects, like if we have, like let's just say we have to add a vector that looks like that, and that, then we can add these vectors in any order because addition is commutative, which if you don't remember what that word means, it means we can swap any of these around in any different way. Vectors are the same exact way. So we could say that the addition of these vectors, if we start at this point here, we go up to here, we go down to here, and then we go right to here, which means that the total added vector goes like this. That would be our total vector. So if we were to then take all of this, multiply it by 3, we would draw 3 of these vectors here, and then would say when you do this three times, you end up there. So because it's just a repeat of up, down, right, up, down, right again. So that's a little recap on vector addition, because we talk about that both in pre-calc, and I don't know if it'll pop up on the AP test, but that was a unit we went over. So there we go. That would be kinematics.